So thank you very much, Emanuela. Thanks for inviting me to come along to this conference, which is on the topics that I find truly interesting and I don't work on. So I was giving kind of the title Upcoming Multi-Orbit Spectrographs, and in truthfulness, I will focus on two of them towards the second half of the talk. At the beginning, I will give some background of what has driven the design of some of the aspects of these two spectrographs. We have some excellent talks coming after me on other spectrographs and survey facilities, so there will be plenty of material, I think, to look at. As I see it, so I'm here on the right-hand side of this of this slide. I'm a Milky Way galactic archaeologist. I like to understand why the Milky Way looks like it does and how it became like that. However, of course, it's extremely intriguing to, or necessary, and to answer that question is to start at a higher redshift where we have the chain galaxies turning into spirals, etc. But how do we go from the left-hand side to the right-hand side? And of course, lots of this conference has been on this topic. So I think there is two, or we could call it three ways to tackle this question. So what has been presented this week is really to observe galaxies across time and environment to infer the overall formation and evolution of them. Or, as people like me are trying to do, study the Milky Way and its neighbors in detail with stellar radius and elemental abundances with aiming to try and pull apart what is going on. However, there is also the theoretical or simulations approach, and I just like to highlight, or not highlight, but to give a little bit of a push to recent work here presented by Oscar Agertz and collaborators, where you see simulations that really are reaching down to very, tens of parsecs of resolution. In the top panel, you see evolving from redshift of 2 to 1, how where the cold flows are, the formation, the last major merger coming into Milky Way look-alike galaxies, almost forming out the metal poor disk and so forth. And as you can see in the lower panel, how you go from the blue, lots of blue material here, which is high alpha to Fe ratios, so indicative of mainly supernova type 2, to a medium intergalactic and interstellar medium, which is basically solar, or, well, in this case, a bit, it's higher than solar, but there is, of course, a normalization issue sometimes. But, it really decreases. You're getting a lot of chemical evolution going on in these galaxies simulated. So that's really kind of cool to start to comparing to both Milky Way observations and extragalactic observations. So since I really like the Milky Way, I will take the prerogative to show a few slides about why the Milky Way is a really exciting galaxy to study today. And I think we've also seen some really good examples in the talks where we are getting to the stage where we can actually compare other galaxies of look-alike Milky Ways or properties of other galaxies and compare them to what is happening in the Milky Way. But it's always been very intriguing to me that if you look at this star formation rate of the universe from Maddow and Dickinson, and here I'm then just taking a sample of stars from Bensby et al., we can see that what we often refer to as the thick disk in the Milky Way, which in this case is kinematically defined, is spanning really all these epochs of formation here, redshifts 1 and upwards. So really covering the peak of star formation rate in the universe. The Milky Way thick disk is not thought to be the main component in most studies, at least, of the Milky Way disk. That's mainly the thin disk, which forms later. But we do, in our neighborhood, in our backyard, have the archaeological remains of what happens during these formation epochs here, this peak of the star formation in the universe. And I think that is interesting to try and connect those things. Now, another thing that we can really study in the Milky Way is, of course, how the stars are moving. And I will show a little bit more on that. So theoretically, and you might be familiar with this figure here we have, this is Rock-Rosca's seminal paper from 2008, where you're looking at where stars are forming in a galaxy. This is a simulation. They're forming from 0 to 12 kiloparsecs. But through various processes in the disk, and it's very strong in this particular simulation, you can see that the star that formed at 6 kiloparsecs may now be at 10, 11, 12, or 13 kiloparsecs away from the center of the galaxy. So things are moving a lot. There is two main methods of doing this. Is the blurring, whereby stellar orbits get nobbled. But there's also the churning, which you can learn much more about in the Selwood and Binney paper that pinpointed this particular mood of moving, where orbits are actually just instantaneously altered at co-rotation. The orbit shape is basically kept, but a star that formed further in is now going to be seen further out, or vice versa. Another example of this is Ivan Minsh's work, where he's looking at stars around the solar circle and seeing at stars of different ages, where did they form. So the red one are the oldest ones. They really formed much further in, like 4 kiloparsecs rather than 8 kiloparsecs, and they have been churned to here, most of them, because you cannot find methods of blurring the orbits sufficiently that they would move out to us. And also lots of these are on circular orbits. So that's something you can study, and I believe that this is, you can call this secular evolution. You can start to see that in other galaxies and deconvolve the different stellar components with the Schwarzschild modeling of the orbits, etc. Just want to then further, because I'm going to build up the case for why we need these multi-orbit spectrographs in the Milky Way case. I think you have all already shown us why we need it for the extragalactic case. Gaia is ESA's highly successful astrometric satellite, which was launched 2013 and has obtained proper motions and parallaxes for more than 1 billion stars in the Milky Way. Every dot you see in this image is a star. And you see the Large Magellanic Cloud and the Small Magellanic Clouds. And further data releases will give us higher precision in these measurements. Something really unexpected came when people looked at just the stars that have a high tangential velocity on the sky. You have the Hirschsprung-Russell diagram here, and as you can see, there are 2 sequences in this Hirschsprung-Russell diagram. These are stars that are moving like halo stars. There was no knowledge that this existed whatsoever in the Milky Way before. So I point you to Amina Helmit's excellent annual review on this particular topic, but there's a big merger here in the past hiding. But actually, to really understand these type of things, we really need something more than Gaia, because Gaia gives us the proper motions and radial velocities for maybe 2 billion stars, and it does give us, it doesn't give us radial velocities for more than, the brightest 15% or so, which is a stupendous data set, but it's still very small. So there are the elements, of course, as you know, are formed in stars. Different elements come from different types of stars. As we say, I talked about the alpha elements forming in the core-collapse supernova, while iron is formed in the degenerate supernovas. So by measuring elemental abundances in stars, or rather in their stellar atmospheres, we can either find out where the elements came from, or, as I'm more interested in, and you are as well, use the elements to trace the history of the Milky Way and its stellar populations, or in other galaxies, trace what has happened to the stellar populations over time. And so when you do that for something like this Hirschsprung-Russell diagram, which is two sequences, actually, well, once you fully have 3-dimensional kinematics, you can go into complicated kinematic spaces with the angular momentum and the actions and identify a really pure kinematic population that is this galaxy. If we then take from one of the largest currently available elemental abundance studies surveys, the Apogee, and now we have a quite complicated abundance space, and I will not dwell too much on it, but it's magnesium over manganese as a function of aluminium and iron, and the sun is at 0, 0 here. And when you put stars with different identified by kinematically, you see that the thin disk falls down here, thick disk is falling up here, and there is a bunch of stars that fall up here. And they are accreted stars, and we actually don't know quite why aluminium is a good tracer of accretion, but it does appear to be so. This is not just found for this, it's also found for the Sagittarius dwarf galaxy, for example, which also falls in this space. So by adding elemental abundances, we can either, jump this stage and actually find them directly, or we can learn more. So that is one thing that has been driving our wish from the galactic archaeology side to have these large spectroscopic surveys. And here I'm just comparing 3 of the ones that are observing in the optical, that is either has, or 4 of them, one Gaia is done with the flames on the VLT, Galar with Hermes, and the 2 that I will spend a lot more time on soon, Weave and Foremost. And as you can see, we have very blue, doing the calcium H and K, strontium and the G band, and then magnesium B, and this is in Weave. You can flip between these 2. So this magnesium B is that really for people who are doing galaxies rather than the Milky Way, and then something around H alpha and below. You guys are probably more interested in this plot where I'm comparing and showing you where Foremost and Weave are sitting in comparison to other well-known spectroscopic survey machines such as BOSS, Taipan, the PSF, where we'll have talk soon, DESI, Segway, and then we have resolutions of typically 5,000 and above in Foremost and Weave. So now let's turn to these 2 facilities and compare and contrast them. So Foremost is a multi-object spectrograph to go on the Vista telescope on Paranal, and Weave is a multi-object spectrograph and IFU to go on William Herschel telescope on La Palma. In fact, the whole spectrograph is on La Palma already. Foremost is being currently built. Foremost is built to complement major imaging surveys such as the Euclid LSST for cosmology, High-energy sky for ROSITA, galaxy evolution from VST Vista, and the galactic archaeology complementing Gaia and Plato. And as you maybe know, 70% of the time goes to the consortium, which will run a consortium survey over 5 years, but there is the 30% that comes to the Chilean and the ESO community at large. The first selection of potential such surveys has been done, and the work to select the final one are ongoing. Weave has very similar rationale to complement major space and ground-based programs in the current and coming decade. Gaia, of course, but also in particular LOFAR and Aperitif. So with also providing a dedicated wide-field optic spectroscopic instrument in the Northern Hemisphere. Again, consortium run surveys for 5 years, but also then with the community coming in at 30%. So here you see a few key elements that might be of interest. And of course, there is a lot more, and there will be web pages to look at. Field of view, diameter roughly similar, 2.5, 2. Here we have 800 high resolution fibers, 1600 low. Here is 1000 either low or high resolution. However, this is in a Echidna fiber positioner, and this is a pick and place fiber positioner, which means that for Foremost there is a configuring time of about 4 minutes or thereabouts. It depends a little bit on overheads. While for Weave there are 2 plates with 1 hour allocation to allocate all the fibers. But it also has a large IFU and 2 20 mini IFUs for follow-up of galaxies and galaxy properties. Well, there's no IFUs, Foremost just has fibers. So I will run through 2 example science cases very quickly with the top level statements about what the surveys are for both of these. And there is then ample space to read about them more. And I think we also have in the audience some people who are quite knowledgeable probably about some of them, and please step in later to tell us more about them if you wish to do so. STEPS with Weave is the stellar population, that's intermediate redshift survey with about 40,000 galaxies over 25 square degrees and large lambda coverage, which here is important. And they are tracing, of course, what physical mechanisms drive the star formation histories of galaxies, and is quenching over 2/3 of the life of the universe. What is the role of environment versus intrinsic galactic properties in this evolution? So we're coming back here to things like secular evolution, how are stars moving inside the galaxies, and how do the galaxies assemble their mass during the last 7 billion years, which is also something that we are now tracing and looking at in the Milky Way in details, and also in these cosmologically informed simulations like those by Oscar Argett. Weave Aperitif is IFU follow-up of these not exactly sure how they're going to down select here, but anyways, a large survey where they take advantage of the high resolution spectroscopy in the green and in the red with the high resolution, and then the full wavelength for the lower resolution, looking at regular galaxies here with SDSS and the large IFU, and then perturbed galaxies, for example, with a mini IFU. In foremost, there are currently 10 surveys defined, of the five are extragalactic in their nature, and one of them is waves, and I think we have people here who know more about waves than I do. Led by Simon Driver and Joe Liske, and this is to study the growth of structure, mass, energy on scales of 1 to 10 1 kiloparsecs to 10 megaparsecs over the 7 gigayear timeline. So there's some numbers here that come back often in many of the surveys. They will look at 1.6 million galaxies or so in the linking the low and the higher intermediate redshift. And down here, you can see from their paper in the messenger, the limiting magnitude around 21 in AB and 10 to the 2, 10 to the 3 square degrees, sorry. I should say future here are red and black is existing. And then we have waves, which this is
5 minutes.
Thank you. There is the active galactic nuclei survey, which is really a follow-up from the ROSITA for a highly complete census of active galactic nuclei of a large fraction of the sky, basically all the sky that is available to our German collaborators, to study the physical properties of up to 1 million supermassive black holes and constrain the black hole cosmic evolution and clustering properties, and explore the connection between active galactic nuclei and large-scale structures over a large redshift range. Again, is the PA is Andrea Meloni, and there is a paper in the messenger. Just would like to, before finishing off here, to say a few words about Foremost. Foremost survey strategy is actually quite different because Weave is a bit more classical. You have a number of surveys, again about around 10, but there will be, you know, plates that will be basically doing galactic surveys, others that do in extragalactic. You try to compromise and put you all together. Foremost has a different idea in that all surveys are always considered for every pointing at any given time. So you need to stock in all the survey catalogs from the science team, shake them in a big simulator, then you get, and I'm not showing you the plots, these are just the galactic ones, but you know, you get the number densities, the required fiber hours, etc., etc. You can follow, you simulate the whole 5-year survey with an automated way of assigning fibers to targets that are available in the field. So it's not like we say that on the 25th of July, we will be observing open clusters. No, open clusters, waves, AGNs will all be observed together in the same field, in the same exposures. And so that simulation, which is rather, you know, takes a lot of effort, means that you will be running a whole survey program with all the downtime and all that sort of stuff. And that is what we will put on the telescope into this observing queue on day 1 and follow through for 5 years. So there's not like after 2 years you review and see if what is being met. Of course, if there's something going wrong, we will have to change. But the aim is to be able to know when we go to the telescope what we can and cannot do, and do what we have proposed to do. The community surveys and the Chilean surveys will be coming in soon. And then that will be taking place, optimization of the survey strategy very much during next year. So both of these 2 instruments and survey facilities and the operations of them is done by 2 quite large teams. To the left, you have Foremost, and to the right, you have Weave. Weave is in the north, Foremost is in the south. In galactic scales, it's very complementary. You have the PIs as well here, mentioned Rudolph de Young and Gavin Dalton. There is a whole series of messenger articles that I recommend for anyone who wants to familiarize themselves with Foremost, and an excellent website that takes you through everything, facility, observations, team, etc. Weave has a web page as well, and it's hidden under here. It will be on the Xanadu that you can click on it. It's very long. The science cases are in a nice document that is presented on that page. Foremost is on the current schedule starting in 2023. And as I said, Weave is already on La Palma up at the telescope, and it starts in 2021. And so I think the future is really bright here. We're having, the high redshift observations, the low redshift observations, the modeling, the Milky Way surveys, all helping us to understand how galaxies like the Milky Way form and evolve through the ages of the universe. And we already have good tastes of what this can be observationally, but I think in the coming decades, this will really come really to fruition. However, there's one thing I would like to make a plug for which probably this audience is not going to feel very enticed to do something, but if you have ability to support work on understanding our stars, that is actually underlying all the work we are doing. This is just to scare you a little bit, because if I take stars of different temperatures, so a dwarf star and a giant star in a globular cluster, the difference in elemental abundance is about 0.2 dex, because of they have the same elemental abundance, but what you measure in the stellar atmospheres is different due to atomic diffusion. We need to understand these type of things to better constrain, to better understand the observations we get out of our excellent future and ongoing facilities. And with that, I thank you for your attention.